Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 86 in our incredible new tutorial series where you're learning how to think like an engineer using the Arduino Uno R4 Wi-Fi. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons, and in this class we will be using the Sunfounder Elite Explorer Kit. Now, hopefully most of you guys already have your gear, but if you don't, take a look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to teach you is how to use a 3-axis magnetometer to create a digital compass. Now, it's going to take a couple of lessons to get there where we're going, okay? But we're going to start today, and we're going to start today by turning on our magnetometer and beginning to get readings from it, okay? And then what your homework assignment is going to be is to take those magnetometer readings and to calibrate the magnetometer a lot like we did the BMP, a lot like we did the MPU 6050 a few weeks ago. The accelerometers on there we calibrated. So let me get out of your way and let's kind of catch up with how we got where we are here. So what I'll need you to do is go on over to the most excellent www.toptechboy.com, and let's just remember where we left off last week. Remember, we are working with the MPU 6050, the MPU 6050 IMU on the GY87 module. Now, so far on the MPU 6050, we know that it has 6 sensors, 3 accelerometers and 3 gyros, and we have fully programmed up those accelerometers and gyros. So the MPU 6050 is working properly. This was the code that we ended up with last week here, and you can find that at www.toptechboy.com. You can use this search icon. You can search on something like improving MPU 6050 IMU by using a complementary filter. So what we did last week is we took the best things about the accelerometer and combined them with the best thing about the gyros, and we ended up with a little widget that would very accurately measure pitch and measure roll from the MPU 6050, and we got those accurate measurements by using a complementary filter, okay? And the results that we ended up with, just sort of where we again ended up with last week. This is the output of the program. I'll show you here. This is our little device, and so if I roll, let's see, I need to probably reset this. Let's see if it'll kick on here. Okay, there it goes. So if I roll, the roll is shown in blue. What do you see? It's fast, there's no drift, it's accurate, and it's not susceptible to noise. You know, noise and vibration don't lead to a problem with the signal. Same thing with pitch. I can accurately pitch and I can accurately roll. And I got a little glitch there, so let's reset the thing and let it start again. Okay, there it is. So I can roll and I can pitch and things are working great. Okay, so why don't we just stop there? It's like life is great, everything is wonderful. Why don't we just say good enough? Well, remember that the yaw, like what we're getting in yaw right now, and yaw is moving it this way. Okay, you see we're getting a nice signal. The yaw is in green. Okay, let's let it go. Okay, so you see I'm getting a very nice yaw signal. But remember, for the yaw, we are only using the gyro because turning like this, you do not see the Earth's gravitational vector because the gravitational vector is going straight down. Now, on pitch and roll, we clamp the reading to that gravitational vector, so we get a very, very precise roll and pitch. But in yaw, we cannot use the accelerometers because they do not see the gravitational vector as you rotate like this. And so we had to just use the gyros. Well, that looks great, right? You look at the green and it looks great. But the problem is we know that those gyros drift over time. So if we just sat and watched this, we would see the thing drift off. So for roll and pitch, we have those values clamped to the gravitational vector. What we need to do is we need to clamp that yaw measurement to the Earth's magnetic field. We will be able to do that by turning on the magnetometers, okay? So where are we going? We're going to get the magnetometers up and running today, okay? Then next week, you're going to have your magnetometers calibrated and able to measure a yaw, okay, based on the magnetometer data. And then we're going to take that and we're going to fold it into this code. But I don't want to carry along this code for the next few weeks because we're just at this point trying to get the magnetometer to work. Does that make sense? I hope it does. Okay. Now, sports fans, you are in great shape with your little GY87 module. Some of you guys bought the Sunfounder kit. That's great. Some of you guys had a lot of the components, so just ran out and bought the little GY87 module, maybe off of Amazon. And the stuff we did with the BMP 180, the pressure sensor, worked great for you. The stuff we did on the MPU 6050 so far has worked great for you, the accelerometers and gyros. But now we're going to turn on the magnetometers, and that's where there could be a little bit of an issue if you are not using exactly the same component that I am. Now you might say, I ordered the GY87 off of Amazon, I'll be fine. This is the problem. Some of the GY87s, like mine, the one in the Sunfounder kit, have the QMC 5883L magnetometer on it, okay, the 3-axis magnetometer. Other GY87 modules have the HMC 5883. And that is very, very similar, but it is not identical. And the I2C address on the HMC 5883 is not the same I2C as the QMC 5883L. And so if you follow my instructions today and in the next few weeks, and you are not using a GY87 with the QMC 5883L, your program's probably going to crash because it's not going to be able to find your magnetometer module because your I2C address is different. So if things are behaving, in an unusual way, it's probably because your GY87 is not identical to mine. Now, what you would want to do is you would want to go to Amazon. These things are only like $5 or something, so it's not that much. But you would want to go to Amazon. You would want to order another GY87, and you would want to look and very carefully read and make sure that the one that you are ordering, has the QMC 5883L on it. I am doing way too much talking, but I just know you've been chugging along in this class and things are going great, and you might have a little bit of a setback. You might have a little bit of a setback if you get in there and then you find that your magnetometer isn't working using the things that I'm teaching you here. Enough said. Way too much talking, not nearly enough engineering. So let's jump in and let's think, what is our strategy to be able to make a compass where we can measure heading, or as we called it in the other program, yaw, right? Yaw or heading or magnetic direction from those magnetometers. Okay, so how would we do that? Well, let's always start with a circle. Okay, let me get a circle going here. See what we can do. Wow, a beautiful circle. Okay, now let's think on this circle as if it were a compass. I also need to tell you before we go any further, if you look over here on my setup, you saw on Top Tech Boy how I've got it hooked up. But with your GY87, if you look at it very carefully, this is the X direction and this is the Y direction. Well, I want to orient things with this being where I'm measuring, and so this would be like the needle of a compass. And if we're looking here, I'm lining up forward and front with the x-axis like this. And so this would be north, and then if I'm coming this way, I'm coming east. And so I'm measuring everything relative to the x-axis. Okay, so what is going to be happening? Let's think in simplified terms. The Earth's magnetic vector is a horizontal magnetic vector going from north to south. Just like gravity goes up to down, I've got this magnetic vector that is coming in from north to south. Okay, and so let's just draw here, and let's say that this is north, okay, and then this is east, and this is south, and this is west. Well, if I point my x-axis and line it up, I line my x-axis up with north, then I should see my maximum magnetometer reading on X. The X magnetometer should be a maximum when I am pointing north. Now, as I swing towards 0, that X magnetometer, as I swing towards east, that X magnetometer should go to 0, because if the vector is coming in north and my X magnetometer is pointing east, it won't see it. It should see 0. Now, as I come south, it should read negative of what it was reading when it was north, and then back to 0 and back to its maximum value when you're pointing north again. Okay, now that's what it would work like. That's how it would work in a perfect world. Okay, so let's say that I am pointed my x-axis like this instead of north. Okay, that I've got my compass tilted. Well, there now I'm going to get a reading on the X magnetometer, and I'm going to get a reading on the Y magnetometer. Why? It makes a triangle, right? And so this would be the X magnetometer reading, and this would be the Y magnetometer reading, okay? So the Y is going to see the magnetic vector, and the X is going to see the magnetic vector. Now, I have some heading angle or some yaw angle between being at perfectly north and being where I am. And the question is, what is that angle? What is that heading? Well, I calculate it from my X value and my Y value using what? Who is your friend? Trigonometry. What did we learn in high school? SOHCAHTOA. TOA, tangent is opposite over the adjacent. Okay? And so what we know is the tangent, or what we could say here is, let me say that more clearly. Okay, that the tangent of that angle is going to be equal to the side opposite. And what is the side opposite? This is opposite Y. And then adjacent is going to be X. So X is adjacent to the angle and Y is opposite the angle. And so the tangent of theta is going to be the opposite Y over the adjacent X. Now, what is the problem? I'm not trying to figure out tangent of theta. I'm trying to figure out theta. So I want to solve for theta. So what do? I take the tangent inverse of both sides. On the left, the tangent inverse of the tangent is just the angle. And then on the right, I have the arctangent, A tan, that's undoing the tangent of Y over X. I did that very poorly, didn't I? y over x. Okay, now Arduino, the arctangent function is a little bit complicated, and you got to keep track of what quadrant you're in and all of that. But Arduino has an arctangent function that keeps track of all the quadrants and signs that is very, very helpful. And so what we would do is in Arduino, we would say the angle is the atan 2 of y comma x, which is just numerator comma denominator. All right, and then with this equation, we can take the y value that we measure and the x value that we measure. We can calculate theta, and that is our heading. How many degrees clockwise from north is my widget pointing? How many degrees clockwise from north is my widget pointing? So that would be a digital compass, and that is what we are working towards. That is what we are working towards. Okay, now let's do a little bit of bookkeeping here. And I think I've talked about what we're going to do. I've talked about our strategy. I've talked about all of that. And so maybe now would be a good time for us to actually come in and see if we can start coding this thing. Okay, and if I think of something else I should tell you, I will, but let's go ahead and kill this thing. And then let's bring up a fresh new IDE, which we have here. And then let's see if we can kind of start getting this thing coded up. Okay, now, first thing we got to do is we got to load the library. So we're going to come over here, click the little library icon, and then what is our device? It is the QMC5883L. You need to search on that, and then what you can see is you come up with the QMC5883L compass by M Programs. Okay, very, very good. You see that I already have it installed, but you need to install it. And note that I'm using version 1.2.3, and it's usually a good idea as you're learning something to try to use the same version of the library as I am to at least get it working. And then what you can do is later you can come in and you can update the library if there's a reason that like a more recent one works better. Okay. So now, what do I want to do? I want to come to the QMC5883L that's sitting on the GY87 module that is connected according to this schematic that we've been using in the last few lessons, probably the last 7 or 8 lessons. And so your circuit hasn't changed, but now we're going to turn those magnetometers on. We installed the library, right? You installed the library. Now we're ready to start coding. So we want to load in the libraries. So we're going to start to include Adafruit underscore MPU 6050.h like that. Now, you might be saying, hey, I thought we were working on the compass. Why are you loading in the library for the MPU 6050, which is the accelerometers and the gyros? We're not using the accelerometers and gyros. That's true. But to get to the magnetometers, you have to turn the MPU 6050 on so you can get over to and see the magnetometers, even though it's a separate module. So it's almost like the magnetometers are kind of like a underneath or after the MPU 6050. So you got to turn this on. Now, if you just have that, if you just have the magnetometer without having the GY87 and the MPU 6050, you wouldn't have to do this, of course, all right? But for us, we have to do this. And also, we have to include the sensor library for Adafruit, because this is needed to turn on the MPU 6050, and that is sensor.h. Okay, and now finally, we're using I2C, so we are going to need to include, wire.h, like that. And all this is the same as we did last week. We load this libraries in, and now we get down to business. And our business is we are going to include the QMC 5883L compass.h, like that. All right, we've included our libraries. I'm going to go ahead and run that just because I want to make sure that I have those libraries installed. Now, if you're a drive-by shooter and haven't been here for the last few lessons, you will need to install these two libraries. I think if you just install the Adafruit MPU 6050 like we just did for the compass, that it should install the dependencies, which would probably include this one. Okay, but let's run this thing and make sure that I don't have a typo, that I can load the libraries. I like to take the little victories where I can, you know, like just do a little coding, run it, build your confidence up, if you know what I mean. Okay, now when we do our readings, we're going to be doing readings, right? So I'm going to read into an X value from the magnetometer, a Y value, and a Z value from the magnetometer. Those will be integers. Now, remember, in order to get over to the magnetometer, we have to have the MPU 6050 running. So I have to do the library Adafruit underscore MPU 6050, and I'm going to create an object MPU, even though in this program I'm not going to be reading the 6050. Now we get down to real business. We're going to use that QMC 5883L compass library, and I'm going to make a what? A compass. Okay, like that. So now I have created my compass, and I should be able to talk to it because the MPU 6050 is alive and happy. So now we're going to come to the void setup. We're going to do a serial.begin, and this time we're going to do a 115-200. Why? Before this thing is over, we're going to be sending data from both the magnetometers and the gyros and accelerometers over to Python on the desktop, and so we're going to be sending data at a pretty good clip. So we want to have a pretty fast baud rate, so our serial connection can keep up. Now we're going to need to start that MPU that we built. So we're going to do an MPU.begin. And then this again, we're getting down to business. I have to tell the MPU to set I2C bypass to true. So this is telling the MPU 6050 to allow the microcontroller to go past the MPU 6050 and to talk to the QMC 5883L, the magnetometer. Now you can use the MPU 6050 and the magnetometer at the same time, but if you are going to be using the magnetometer, you got to make sure that you set this line of code. So now everything should be copacetic, so we are ready to compass.init. Compass is the object that we created. We are going to init it. Just for good measure, let's make sure this thing still works, right? I like to make sure that I don't have any just silly typos in there at this point. Okay, that's looking good. Okay, so now we're going to be down in our void loop, and what we're going to want to do is we're going to want to do a compass.read. So we're going to read from the compass. That's pretty straightforward. Now we're going to say X is going to be equal to compass.getX. All right, open, close, and then Y is going to be equal to compass.getY, like that. And that needs to be a semicolon. And then we're going to do a Z is equal to compass.getZ, open, close. So now we've got our X, our Y, and our Z. I don't want to forget that we need a delay in here. So I'm going to put a delay of about 1/10 of a second just so that we're not hammering that module too quickly. But now I've got X, Y, and Z, so I'm going to do a serial.print. And what I'm going to print, I'm going to print X. And then I'm going to do a serial.print. I'm going to put a comma in there. So the comma is going to be my delimiter, like that. And then a serial.print. And then I'm going to print what? You guessed it. We're going to print Y. like that. Okay, now I'm going to do a serial.print, and then we're going to do our other comma, our other delimiter, right? Don't forget that semicolon up there. Okay, and then I'm going to do a serial.print, wait for it, ln of z. So now it's going to print the x magnetometer value, the y magnetometer value, and the z magnetometer value. Those are the values that we are going to print out. And then it's just going to be x, y, z. And now hopefully this thing will start spitting out data. And then as it spits out data, we're going to sort of see what it looks like. So I'm going to go ahead and I am going to run this, and hopefully it's going to download, and hopefully it's going to print out something other than like zeros or -1. Hopefully it's going to print values that look, like real sensor measurements. And so this is looking good. And now let's turn on our serial monitor and look at that. Boom, X, Y, Z, and they're numbers that are not 0. And so these are the raw readings that are coming from the accelerometer. Now, magnetometer, magnetometer, magnetometer. I should not have said accelerometer. Okay, now I want to start seeing how those things vary as I move this around. But what I got to start with is I've got to start with kind of knowing where north is. What do I expect? I expect my X value, the value here, to be a maximum when I align this so that X is pointing north, because there X would be seeing the full brunt of the Earth's magnetic field, because X is perfectly aligned and Y is not seeing it at all because it is orthogonal. So I want to kind of check that. So what I want is I want to know where I am. So this pad here, I want to orient it to where these lines are pointing perfectly north. And the way I can do that is, you can use a compass, or my iPhone has a compass on it, and I have the iPhone to point to magnetic north, right? There's a difference between magnetic north and geographic north. In other words, the compass doesn't point exactly at the North Pole. Magnetic north is not exactly at the North Pole. And so what I have here is I have this going, and you kind of are getting some glare on that. I'm not sure you're getting glare from my studio lights, but I'm lining my iPhone up perfectly with the lines on this pad. And now I want this direction to be north. And so I rotate this until the pad is pointing perfectly north. I want to make sure the iPad is on there good. I also want to get my magnetometer and Arduino away from the iPhone because it can be doing a little interference. Okay, and there I am reading perfectly north. So now I take the iPhone away. Now this iPhone will mess up the readings off of this iPhone will mess up the readings on your magnetometer here. So you want to get the iPhone all away from it. Okay, so now where are we? I'm trying to get this cord. As I'm spinning this thing around, it's a little bit hard to do the cord management. Okay, so there. Now, I am lining this up perfectly with the lines on the pad. And so at this point, the magnetometer, the x-axis of the magnetometer, is pointing exactly north. All right. And then let's see here. I think I need to get my wires plugged in really good. Everything's secure. I need to reset this. Okay, and now what am I reading? I'm reading a value of about 340 as I'm pointing due north. Okay, and then as I turn it, it starts going down. Why? Because now the x-axis of the magnetometer is not seeing the full value of the Earth's magnetic field. You see, I come up And when I'm perfectly north, I'm reading something about 380. Okay, 380. Now, as I start pointing east, and you're watching the x value, that's all we care about right now is the x value. Now, as I begin to turn it, I'm seeing x go down, 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 because I am not seeing the full vector. And you see it's even gone negative now. And when I point east, it is reading a negative number. All right. But now when I point all the way south, it should be at its absolute minimum, which is minus 1200. And then when I'm pointing east, it's about minus 400. And when I'm pointing north, it is about 400. Okay. Now, what does that mean? We have to think about what that means. And in order to do that, I need to come back over here. All right. Now, if in a perfect world, for my math and everything to work here, what do I need? What I need is the circle of values of x and y values as I turn the project through the 360 degrees, just like I did. In an ideal world, it would form a circle centered at 0. But if we look at it, we are not getting a circle centered at 0. Like if it went from plus 300 to minus 300, that would be great. But we're not getting plus 300 to minus 300. What we're getting here is, right now we're getting about 300, and then as I rotate it, I am getting like minus 1,000. So what does that mean? That means I have a circle, but it is offset down. I have a circle that is offset down. Now, similarly, if I come here, now I'm going to point y. I'm going to point my y perfectly north. Now, this should be a maximum value for y. This should be a maximum value for y. And what do I see? I see minus 400, and that should be my maximum of y. And now as I turn it around, or actually that is a minimum, so the positive y is going this way. So this is the positive x, this is the positive y, and so I think z would be down. But now when I point y this way, maybe I'm just confused. Yeah, I am confused. Okay. So this is y, that's the second number. All right, yeah. Okay, so this is y. We're looking at the second number here. Now y is pointed due north, and when y is due north, it's a maximum y value of about 1,000. Now as I turn it around, it gets lower and lower and lower and lower, and then here, it's a value of minus 500. So that means that my circle, instead of being at 0, 0, is down and to the right. And so instead of having this beautiful circle, I've got a circle that is down and to the right. And I also don't know if it's got the right size, and I don't know if it's round. And so what I really might have is something like this, and what do I have to do? I have to turn it into something like this. So what two things do you need to do? You need to take from here to here, and you have to take your raw data, and you have to apply an offset in x and an offset in y to get this center point to the point 0, 0. Now at that point, I'm going to have something maybe like this, which might not be round and might have a scale error. Now what I've got to do, I've got to make this go to +1 to -1. Okay, so I have to bring that out. That is a what? A scale error. And I have to take this and take that 1 to -1. Now this is just like we did on the accelerometer, right? I'm just kind of repeating what I did on the accelerometer. But you can see there's 2 errors right here. There's 2 errors in my data. There is an offset error, which I do by finding this and moving it here. I correct the offset. Then once it's here, I have what? A scale error. All right, so I have an offset error and I have a scale error. This is just repeating what we did on the accelerometer, right? And so what I've got to do is I've got to find the center of my raw data, and then I have to calculate the offset that I need in order to get the center at 0, 0. And then I have to say what is the maximum and the minimum value and what is that range, and I've got to set that range to 1. And then what is the maximum y value and the minimum y value, and then I have to set that to +1 and -1. So I take this kind of odd, maybe not perfectly round and not the right size offset, and I've got to map it onto the unit circle from 1 to -1, right? Centered at 0, 0. Does that make sense? I hope it does. And that's what your homework assignment is going to be. What your homework assignment is, number 1, you have to find the offset. Okay. Then number 2, you have to find the scale error. And then you have to apply those to the raw data to get the calibrated. And you're not seeing that, are you? To get the calibrated data. Okay. And the calibrated data should be here. The calibrated data should be here on the perfect theoretical circle. Does that make sense? I really hope it makes sense what I just said. Okay, now we got to talk a little bit more about a few other things that we are seeing, because man, that accelerometer works so perfectly and that gravitational vector is so perfect. But the problem is, or the thing that you need to be aware of is, things are not so clean and easy and perfect when we are dealing with the magnetic vector. Because what I want to show you is, first of all, what do we think? Well, we think that the magnetic vector is just this simple vector coming from north to south that is perfectly horizontal like this, and we're just sitting in this flat plane, okay? And then the thing is, though, if that were the case, if the magnetic vector was truly horizontal, what should I be reading on the Z magnetometer? I should be reading 0 because it was horizontal. But am I reading 0? No. When I'm sitting flat, I'm reading 1500. And then if I turn it upside down, I'm reading 400. And so what I'm seeing is that sitting flat, there is a Z component to the Earth's magnetic vector. Now that is true and it is known. So it is true, and so it should not be a surprise that we are reading a Z component of the Earth's magnetic vector. And in fact, that has a name, and the name is magnetic inclination. Magnetic inclination. And I show it here. And what this shows is, this is declination, this is inclination. And so this shows at different points of the Earth's magnetic field is not 0. It's coming out of the Earth and then it's going into the Earth. And only if you're at the magic spot, do you get a horizontal magnetic vector. And that magic spot here, if you look up inclination, that magic spot is this green line, and there along that green line, you have a perfectly flat, perfectly horizontal magnetic vector. Now, the interesting thing is I am at the equator. So I thought, well, at the equator, I should have a perfectly horizontal magnetic field, a magnetic field from the Earth. But if we look at it here where I am, right about here, I'm on this first major blue contour, and so I'm at minus 20 degrees. And so what that means is the Earth's magnetic vector is not horizontal, it is coming in at about 20 degrees, and therefore that is why I am reading. That is why I am reading that, that Z value on the magnetometer when I'm flat, okay? And even if I centered it and did the calibration, still I'm going to be reading a Z value there, and it's because of inclination. So you need to know the inclination is there. You don't need to include it in the calculation. Right now we're just using Y and X to calculate the angle. We need to calibrate the sensor, and we use the arctan2 of Y comma X, and we should then get an angle, right? We should get an angle then. But you need to know that this inclination is there, and then you understand why you're reading a Z component to your values here, okay? Besides inclination, there's also declination. And what declination is that the magnetic north of the compass is not at the North Pole. So like these magnetic lines are not coming up out of the North Pole, they're coming up out of some area near the North Pole. And how big that area is in degrees, how big that error is in degrees, depends on where you are. And what that is called is declination. Inclination is how much Z there is to your magnetic field, how many degrees it is from horizontal. And declination is how many degrees difference is there from where you are, where the magnetic north is, versus the geographic north, the North Pole. And you can see that's kind of complicated too. Now, you see, it really depends, the declination depends on where you are. And so if you really want the true geographic north, you've got to compensate by the declination angle, by adding it or subtracting it. So let's see where I am right here. You can see I'm between 0 and this contour line. And let's see what that contour line is, what my declination would be. It looks like this one is 10. And so I'm at the first one. So this would be like 2, 4, 6, 8, 10. So my declination is between 2 degrees and 0 degrees, and so that would be like 1 degree. So I'm not going to correct for the declination, because that's just too small to really worry about. But you can see some people, like if you're, let's just say that you were in Texas. In Texas, you're pretty good too, because you'd be about 4 degrees off. If you're up here in certain places, you can see you can get like 20, 30, 40 degrees between your magnetic north and the North Pole. Okay, does that make sense? Now let's go back and look at inclination again. So this is inclination. This is the tilt like this in the magnetic field. And let's say if you were in Dallas, let's say that you were right about here in Dallas, your inclination is 60 degrees, meaning that magnetic field is not anywhere near horizontal. Your magnetic field is getting almost vertical. It's like the magnetic field is coming up and then it's going over and coming back down. And so you have a really large inclination. Again, you need to know the inclination is there, but you don't need to factor it into your calculation at this point. Okay, let me see if there's anything else. What we really just saw is we've got to take this circle that's the wrong size and not centered, and we have to come up with our offset, and then we have to come up with our scale to get a perfect circle centered at 0 that goes 1 to -1, 1 to -1. And then if we can create that circle, then we can do our arctan 2 and we can get our heading. Wow, did I just confuse everyone and make everyone rue the day that they ever took this class? I hope not. One other thing I should show you. Okay, one other thing I should show you before I turn you loose on the homework. Okay, I want you to look at this. I want you to look at this X number here. And you can see these things are jumping around a little bit. Let me start this thing again. I think I need to, I'm just going to, okay, this we're looking at the X value, and you see as I'm oriented here now, I am reading the I'm reading somewhere around 0, and you see now it's 200 or 300. You see it's jumping around a little bit, and it's not a perfect number. But what I want you to watch here is that I'm at like 200, and now I want you to watch as I start bringing this towards the computer monitor. You start seeing that that number is changing. It's getting like bigger and bigger and bigger. And you see I'm not changing the orientation, but as I get closer to the computer monitor, it becomes bigger and bigger and bigger. And now if you watch Y, and I'm getting closer to this other one, it's making it smaller. So what you got to see is your electronic devices around you are going to affect your readings. So when you do a calibration, you need to scoot back and try to be like 5 feet away from any electronic devices. And then what you also need to see, besides being 5 feet away from an electronic device, once it's calibrated and you're making readings, if you're sitting here around a lot of electronic equipment, it's going to affect the accuracy of the heading or the compass reading that you are calculating. So there's a lot of noise and interference in the magnetometer that you didn't have to worry about with the accelerometer and with the gyro. Okay, so what is your homework assignment? Your homework assignment is to calibrate the gyro and then to calculate a heading value based on your calibrated readings, so that when I point it here, I should be reading 0 because I'm north, right? I'm pointing north, and then it should come to 90 degrees, and then it should come to 180 degrees, and then it should go to 270 degrees, and then it should go up to 360/0. So that is your homework assignment. If this wasn't clear, go back and watch the video again where we calibrated the accelerometer, because it's really kind of the same thing we're going to do here as we did when we did the accelerometer. Okay, guys, I hope you are having as much fun taking this class as I am making it. It's at this point that I always give a great big shout out and thank you to my Patreons. If it was not for my Patreon support, I would not be able to continue to make fresh, new, quality, in-depth content every single week. So big thank you for you guys standing next to me. You can also help by giving the video a thumbs up and leaving a comment down below. If you haven't already, subscribe to the channel. When you do, make sure you ring that bell so you'll get notification when future lessons drop. And most importantly, share this video with other people, because the world needs more people thinking like an engineer and fewer people sitting around watching silly cat videos. Paul McWhorter, TopTechBoy.com. I will talk to you guys later.